Hi, Gabe.
Hey, Professor.
Hi, Gabe. How we doing?
Good. How are you?
Oh, peachy keen, wonderful. I think you're the only one in here yet, so we're gonna wait for a few seconds.
All right.
Okay.
Sounds good.
Quiz tough.
Oh my goodness, so hard.
It's the first time you guys have had new material, really.
Hardest quiz ever.
Uh, yeah.
For sure, it was the one that got dropped. Thank God. But it was my
Well,
lowest.
I'm gonna look at it again and see if it was fair or not.
All right.
I thought I looked at it beforehand, and why is this not showing up? Thank you. This is just taking forever. Anybody else in here? Jasmina just showed up. So I'm going to go pull this up. We're going to share screen for a second. Okay. Jasmine, are you in?
Yes, hello.
Okay. I apologize about your test score, right? It was a
no worries.
91. Now it's a 97, right?
Yeah.
What happened is I probably skipped over the question. And I was giving you feedback. And after I gave the feedback, I looked at the score and realized I didn't put something in there. And I basically what it was I graded the question before. It's fixed now. Okay.
Yeah, that's what I figured.
Yeah, so you have that. About the quiz. I'm looking at it. It was quiz 11,
12.
12. Okay. All right, let's see what I did here. I think I know what I did, and I think it was, yeah. Okay. Let's just hold on 1 second. All right. Okay, I'll give you another shot at it. Okay. Fair enough?
Yeah, thank you so much.
No, it's what is fair. Just give me, do not try and take it. Do not try and take it until I get in there, okay? So in other words, give me until 5 tonight, all right? It should be fixed. Okay? Are we good? Kevin, you in? Kevin, you in here?
I'm alive.
Oh, good. I got three people here today. All right, guys. Now, if you could give me a little help as to where we ended. I believe I was just starting calorimetry. Is that correct? Did I go through these rules, the enthalpy equation rules?
Yeah, you went through, I think you went through some of the enthalpy. You started to explain it.
Okay.
If you pull up the slide, I might be able to tell you. I thought you were around like 40 slide, like 40 something.
Okay, this is basically, did I go through the enthalpy rules that enthalpy follows stoichiometric rules? That basically, if you, do you see the slide that's in front of you now?
No, I can't see it. I don't know. I can't see it.
Sorry. That's obviously. Can you see it now?
Yeah.
Did I get through enthalpy? In other words.
Oh yeah, I think, yeah, you did.
Jasmina, Gabrielle, Gabe, did I get through this portion? I don't mind going through it again.
Yeah, I think so.
All right, do you want me to go through it again, or do you want me to just leave it? Because I think, if anything, I think this is the furthest I got. Did I do one of these problems? Did I do the sugar problem?
Yeah, you did this one.
I have that written down.
Okay. Bottom line, if enthalpy rules follow stoichiometry. So basically, if your stoichiometric number is 2 out there, then this is not 890 per mole, it's 890 per 2 moles of oxygen or 1 mole of methane. Does that make sense to you? Does that make sense, guys?
Yes.
If I double the entire thing, and basically by doubling it, I'm saying that instead of 2 moles of oxygen, I'm using 4 moles of oxygen, then that's going to double my enthalpy. Okay? Other thing that's important when we're dealing with enthalpy, it's going to be important when we get into Hess's laws. If you flip the reaction 100%, so if you're making the products, the reactants now, and the reactants now the products, so you're entirely flipping the reaction, the sign of the enthalpy changes. So I went through this problem. We are going to go through another one. And that's basically, and I'm going to move this because I got something that's right in the middle of my screen. All right. Determine the amount of heat in kilojoules given off when you have that many grams of NO2 produced. Okay. Now, strategy-wise, where are we going to have to go first?
Moles.
We have to get moles. And the other thing we have to understand is that because there's a coefficient of 2 in front of the NO2, this number, this minus 114.6, that's per 2 moles of NO2. So if we just keep that in mind, this becomes a fairly simple problem. And that is, all we do is take the grams, turn it into moles by dividing by the molecular weight. Then we take that number of moles times the enthalpy of the reaction, but that is for 2 moles of NO2. That gets us the energy that is released. Are we good with that, guys? Make sense? Are we good?
Yeah.
I need feedback here. Jasmina, Gabe?
Yep.
Yeah, we're good.
All right. One more. If you notice, guys, when I'm doing these particular problems, I'm not doing it the same way each time. I'm asking for different variables. All right. The last one, I asked how much heat would be produced. This one, I gave you the heat. And since I gave you the heat, I'm asking for the amount of grams of copper that are produced. So in this particular example, you get 1.47 times 10 to the 4th kilojoules are produced. But that involves the enthalpy of the reaction of 333.8. That is a positive number. But that is also for 4 moles of copper. Now, just using dimensional analysis, guys, how are you going to solve this problem? Gabe, let's give you a shot at this.
Convert kilojoules to moles.
How are you going to do that?
We're going to do 1.47 times 10 to the 4th kilojoules times 1 mole over 333.8 kilojoules.
Almost. Absolutely almost. Gabe, what's the number in front of the copper?
4.
So it's 4 moles of copper are produced when that much heat is absorbed. Does that make sense to you, Gabe?
So it would be 4 moles over 333.8.
Yep.
Okay.
Exactly. So whatever stoichiometric number is in the equation, you have to put that number in front of the moles when you're dealing with the enthalpy of the reaction. So if the coefficient is 3 in front of your compound, and you want to know how many grams of that compound are produced, you have to take the enthalpy divided by 3 moles, because 3 is the coefficient in front. We good with that now, Gabe?
Yes, we're good.
All right. Now, it's hard to mention. It's like we can't stick a thermometer in these chemicals as they're floating around in solution. We can't do that. It's a lot easier if we use something to encompass our reaction and something that we can measure easily. One of the things that has a very stable specific heat is water. So, and that's water is where 90% of the reactions are done anyway. So what we have to do is we have to measure the heat change of the water, the Q of the water. And then we can apply this to whatever caused that heat change of the water. Now, remember we said that the system is opposite from the surroundings. Basically, what you have to understand about calorimetry is the water is the surroundings. So if we want to get at what's happening with the system, the water's Q is negative to what the system is. Because if the system is negative, if the system gave up heat, that heat had to go somewhere. The heat went to the water to warm it up. If, on the other hand, that reaction needed to absorb energy, it had to absorb energy from somewhere. The energy it absorbed from was the water. So the water lost energy, but the system gained it. That's a crucial understanding in calorimetry. I need to know an affirmative from you that you're understanding what I just said. And I'm getting nothing. Are we understanding, guys?
I'm trying to. I just trying to look at the
Okay.
book and trying to understand it.
All right, Gabe. You have just been out jogging. Okay, you've run a 5K. All right. You're coming from out jogging. You've been sweating, right? Is your body hot?
Yes.
So you come into the air-conditioned room, right?
Right.
Eventually, does your body temperature come to the same temperature of the room?
Yes.
All right. So what happened was you were giving off energy, and the room's air conditioner had to work a little harder because you gave up that heat energy. The room absorbed that heat, and the air conditioner had to kick on to take that heat away to maintain the same temperature. Is that kind of you understanding that, Gabe?
Yeah, kind of. Oh, yes, yeah.
It's easier, Gabe, it's easier to measure what's happening with the water, because all you got to do is measure the mass of the water and measure the temperature before you did anything in the water and after you did something in the water. Once you do that, then you've got your change of heat in the water. Does that make sense, Gabe?
Yes.
Now that change was affected by what the system did. If the system gained energy, the system had to gain that energy from somewhere. It gained it from the water that was surrounding it. If the system gave up energy, then the water had to accept the energy that the system was giving up. So indirectly, we're measuring what's happening with our system. Jasmine and Kevin, we good with that?
Yeah.
Gabe, we okay?
Yeah.
All right. Yeah, just basically went through these couple slides here. Now, I go through this analogy each time I teach this. Jasmina, have you ever cooked anything in the oven? Have you ever used an iron skillet, Jasmina?
Yes.
All right, you have that iron skillet in the oven. You take it out. Are you going to touch that iron skillet until about 30 minutes have gone by?
Am I going to touch it before?
Yeah, are you
No.
going to touch it when it comes right out of the oven?
Nope.
All right, on the other hand, you're cooking a hot dog under the broiler. You put a piece of aluminum foil down there, or you're heating a piece of pizza up. Okay? You take that foil out of the oven, you move the pizza to your plate. By that time, is that aluminum foil cool enough so that you can crumple it up and throw it in the trash?
I'm actually not sure. I've never really paid attention. Maybe.
So what you're saying, Jasmine, is you've never cleaned up after yourself.
No.
Kevin, Gabe, do you know what I'm talking about? Can you crumple aluminum foil up soon after you've taken it out of the oven?
Yeah.
Yeah.
All right. That means that the type of substance, since you can't touch the iron, but you can touch the aluminum, the type of substance has something to do with the way the heat is absorbed by that substance. All right, keep that in mind. Kevin, if you are feeding your entire family, I'm talking about not the extended family, cousins and all, and you're making spaghetti, are you going to have to use a big pot to cook it in?
Yeah.
Huge pot, right? On the other hand, if you're just cooking it for yourself, you got one of the Velveeta mac and cheese things, and you're only using a quart of water. Which one is it going to take longer to heat to boiling? The quart of water or the huge one you're doing for your extended family?
Big one.
Okay, so the mass has something to do with the way the heat's absorbed. Gabe, you have a bathtub full of water. Okay, you got it just at that perfect temperature that you can put your little tush in there and just feel comfortable. Okay. Now, is it going to take more heat to put it to that perfect temperature, or is it going to take more heat to bring it to boiling?
Wouldn't it be both? Wouldn't it be both?
If you're taking the temperature only to bath water, as opposed to taking it to boiling.
Yeah. Oh, it would take more energy to go to boiling.
So the difference in the temperature also has something to do with the amount of heat that is absorbed. So bottom line, the heat that's absorbed, the Q, that's going to be equal to the mass of what you're heating times the specific heat. The specific heat's a constant that deals with the type of substance times the temperature change. So Q is equal to mass times the specific heat times the temperature change. You might have seen this as MCAT, MC delta T. Do you remember MCAT from intro? I'm getting crickets here, guys.
No.
Doesn't matter. Just understand that this formula can be different from the form I have it here. It can be seen as M times S times delta T or M times C times delta T. The S and the C are interchangeable. Some people like to use a C. Some people like to use an S. I like to use an S because I want to deal with the specific heat of the substance. What I use the C for is the constant for the calorimeter that we're going to get into in a few minutes. But bottom line, does this formula make sense to you? Does it make sense?
Yeah.
Yeah.
All right. Now, the number is also important. If we are dealing with water, and water is 90% of the formulas that we use in calorimetry, because most of the reactions occur in water. So if we're dealing with water, the specific heat of water is 4.184 joules per mole Kelvin. Or I'm sorry, that should be grams Kelvin, 4.18 joules per gram Kelvin, or it is 1 calorie per gram Kelvin. And if you think about this, mass is in grams, so the grams are going to cancel. And I'm going to take this out because it's bad. Grams are going to cancel because the grams and the constant are in the denominator and you're multiplying by grams. And centigrade, degrees centigrade is going to cancel because we are dealing with centigrade as our temperature. So the only thing that's left is the joules, and that's what the label of Q is. Let's see. Unimportant slide. It's just what the definition of what heat capacity is, and that is just the temperature needed to raise 1 kilogram or 1 K. The amount of energy needed to raise the temperature of a substance by 1 degree Celsius or K is its heat capacity. The specific heat capacity is the amount of energy needed to raise 1 gram, 1 degree Kelvin. And I don't even know why they really use Kelvin. If I'm dealing with delta T here, I'm taking the final temperature and subtracting the initial temperature. Do I need to convert to Kelvin? Do I need to convert
No.
to Kelvin?
No.
Because if I convert the temperature final to Kelvin, I would have to add 273 to that. And then I'm subtracting the initial temperature, which I took to 273. So whenever you have a change in temperature, you do not have to convert to Kelvin. Otherwise, do that. So basically, the specific heat is going to be the heat transferred divided by the mass times the temperature, or conversely, mass times change in temperature times the specific heat is equal to Q. Calculate the amount of heat required to heat 105 grams of silver from 10.2 Celsius to 25.8 Celsius. What are we going to do, Kevin?
I have no idea.
Kevin, what's the what are we heating, Kevin?
105 grams of silver.
We're heating the silver. It weighs 105 grams. So what are you going to put in for the mass, Kevin?
105.
The specific heat. Do you have a chart here with silver specific heat?
Yeah.
What's that?
0.24.
So I'm going to take the mass, 105, multiply it by 0.24. Then I'm going to multiply it by what? What was the change in the temperature?
25.8 minus 10.2.
So I'm going to multiply that by 15.6. 105 by 0.24 joules per gram Celsius times 15.6. That gives me 309 joules. Note, guys, that the energy is positive because my final temperature was higher than my initial temperature. You got to keep track of what the final state is and what the initial state is, because that's going to tell you whether your Q is going to be positive or negative. This is positive. It took energy, and this makes sense, doesn't it? Did it take energy to heat that silver up from 10.2 degrees to 25.8? Did we have to add energy in there? If we had to add energy in there, we've added energy to our silver. So the Q is going to be a positive number. Now, if I was going to do water, 105 degrees or 105 grams of water that I heated from 10.2 Celsius to 25.8 Celsius. Look at the difference in the specific heat, guys. The specific heat is 4.184 for water. For silver, it was only 0.2. That's a difference of 17 times. I actually said that. I actually have it right on the slide. I didn't need to mathematically do it. So, literally speaking, think about this. If I have a certain amount of energy that's inputted on your body, all right, am I not dividing it by a bigger number with the specific heat being larger?
Yeah.
So if I'm dividing by a bigger number, if this is bigger, then this has to be smaller. The change in temperature has to be smaller. If the specific heat is larger, since I'm multiplying the specific heat by the temperature change, that means that the temperature change has to be lower because the specific heat was higher. That's why, guys, it's amazing that our bodies are composed mostly of water. It helps us to regulate heat. If our bodies had silver, molten silver flowing through them, then whatever the temperature outside is going to be what the temperature inside your body is, and you wouldn't be able to regulate the heat as well. Water has one of the highest specific heats. It's the highest that I know of. So that's a good thing that our bodies are composed of water. All right. We're going to be doing a series of these kind of equations. Calculate the final temperature. If 255 grams of 25-degree water had 250 kilojoules of energy added to it. The specific heat of water is 4.184. Gabe, remember, Q is equal to M times specific heat times the change in temperature. So, Gabe, what is Q in this problem?
Q is
Okay, let's go the other way.
I know it's heat, but
What is
where-
heat? What is heat? What is heat defined as? Okay, let's go another way. All right, Gabe, do you have the mass?
Yes,
What is
255
that
grams.
mass?
255 grams.
Okay, so our M is gone.
Yeah.
We don't have to worry about that. Do I have the specific heat?
4.184.
So 4.184 joules per gram centigrade. All right, now, do I have the initial temperature?
Yes, 25 degrees
So that's
Celsius.
minus 25. Do I have the final temperature?
No.
That's what I'm trying to find out. So, Gabe, by process of elimination, what is my Q?
250
Kilojoules.
kilojoules.
So, to solve this problem, I'm going to put 250 kilojoules is equal to the mass times the specific heat times T final minus 25 degrees centigrade. I do that math out and I end up with 259 Celsius. Questions, guys? Questions? Kevin, if I take if I take 6,500 kilojoules of energy from a pool of water, does the temperature go up or down?
Down.
Goes down because I'm taking the energy away. The 6,500 is negative. The only way in that equation I can get a negative is for my final temperature to be less than my initial temperature. So the final temperature did go down. But Jasmina, I posed a question here. Have you ever put something in a thermos, Jasmina?
Yes.
All right. Did it stay hot forever?
No.
Why? It's supposed to stay hot. Why do you think the liquid inside the thermos did not stay warm forever? The coffee got cold. Why?
Mm, I don't know.
I don't know is a perfectly good answer. Kevin or Gabe, either one of you have a theory?
Lost kilojoules over time.
Where's it going?
I don't know. Dissipating. I don't know.
Yeah, you're actually right. It is dissipating. But what is accepting that energy?
The mug itself.
Exactly. Exactly. What's happening is the mug, the thermos, is absorbing some of that energy. So we have to account for that as well. So the total energy we have is equal to the energy that the system is changing plus the energy that gets absorbed by the container. So when we're doing this, when we're determining the total energy of our surroundings, that's going to be equal to the heat absorbed by the system plus the heat of the object. So my total energy, my total Q is going to be equal to ms delta T of my solution plus the amount that's absorbed by the calorimeter, C delta T, where C is the calorimetry constant. And that has to be determined experimentally. Are we good with this? Do you understand that we have to account for whatever is containing the water that the reaction is going in? Because isn't that container part of the surroundings as well?
Yeah.
So the total energy is going to be the heat from the water plus the heat lost to the container. When we're doing this, the C delta T, note that the temperatures for the water are the same as the temperatures for the calorimeter. Those temperatures don't change. The final temperature minus the initial temperature is the same for the calorimeter as it is for the water. So again, the total heat is going to be ms delta T plus the calorimetry constant times delta T. The delta T's are the same. And the delta T's are going to always be the delta T's of the water. So another important concept here. Again, remember I said whatever's happening to the surroundings is opposite for what's happening to the system. So the Q of the water is going to be the opposite sign of what's happening in the reaction. A metal pellet with a mass of 52.1 grams was originally at 79.8 grams It's dropped into a calorimeter that contains 125 grams of water at 25.1 Celsius. The temperature at equilibrium is 28.3 degrees Celsius. The heat capacitor of the calorimeter is 45.2 joules per degree Celsius. Calculate the specific heat of the metal. And I'm going to take a sneak peek to see how I did this. I'm not happy with the way I did it, but can we get the total Q? Can we get the total heat?
Yeah.
Kevin, what two things am I going to have to add? What two things do I have to add to get the total Q?
At MS delta T and the temp and the other one, CAT or whatever.
Yeah. Q of the water plus the Q of the calorimeter. Does this make sense to you all? Is this making sense, guys?
Yeah.
Now we have to go back to the problem to figure out what the individual masses are, what the individual things we need to put in here are. So we're doing MS delta T plus C delta T. Okay. Am I doing anything funky here? Am I doing anything at all funky here?
No.
All right. So we have to go back in. Remember, it's the Q of the water. So what is the mass of the water?
$120.
125. No, don't do that. Thank you. $125 times. Okay. Specific heat of water. Have I said it enough? Actually, it's on the page. It's on the page, but it should be a number that should come to you like that.
4.184.
Okay. Now, this is going to be a bit tricky because we have a whole bunch of different temperatures here. What is my final temperature? What is the final temperature of the water?
28.3.
Again, Jasmine and Gabe, we agree with that?
Yeah.
All right. What was the original temperature of the water?
$25.1.
You sure it's not 79.8?
The 79.8 is the metal pellet.
Thank you. You got that, Kevin? Kevin,
Yeah.
did you see the 79.8 was the metal?
Yeah.
You got to be careful what you put in here. So it was 25.1. Okay. What else do I have to add? We also We have to figure out the Q of the calorimeter. So what are we adding there?
It's heat capacity.
What's it?
Times
What, and the
the
number is?
change in temperature.
What's the nu-
45.2.
We have the heat capacity of the calorimeter. That is what your C is. So I'm going to add 45.2. And do you remember what I said the delta T is going to be?
The same as the one for water.
Same as the water. Guys, it's extremely important for you to make sure that you keep the signs correct, that you keep the final temperature and the initial temperature correct in this. I do this math out. And I get key for sig figs, guys. Just for your good to know. Generally speaking, your sig figs are going to be limited. They're going to be limited to the temperature 99% of the time. In this case, our temperature is 3.2, so our final answer is going to have 2 sig figs. All right. Are we good so far? We good so far with this problem?
Yeah.
So we
Yeah.
now have the total Q that was absorbed by the water surroundings and the calorimeter. The question is
Isn't it
asking,
18
What,
Wait, wasn't it
Jasmina?
1840? Wasn't it
Sorry?
1840 joules?
well, specific, we'll figure out the final answer in the end. This is 3.2, right, Jasmina? 28.3 minus 25.1.
Oh,
So significant figure wise,
okay.
yeah, but 1840
Gotcha.
is 1840 is good enough. As a matter of fact, I'm gonna, to get a better answer, I'm gonna do the final sig figs at the end. Okay, guys, all I'm going to do is I know that my final sig fig answer is going to be 2 because I'm limited by the temperature change. So since I'm limited by the temperature change, my final answer, my final answer is going to be 2 sig figs. But for right now, I'm just going to do rough calculations. What do I want to know from this problem, guys?
Specific heat of the metal.
Okay. So I took a hot metal object, put that in water. Whenever you put hot objects into water, the water gains heat. What happens to the heat of the object?
Lose.
So the amount of heat that the metal lost is equal to negative the heat that the water gained plus the heat absorbed by the calorimeter. Does that make sense to you? It all goes back to this thing. The Q of our surroundings is going to be negative the Q of our system. In this case, our system is the hot metal losing heat. So when I get to this point where I have the 1813 joules, this is of my surroundings. My Q of my system is equal to negative 1813 joules. Do you see how I got that?
Yeah.
Guys, do we see how are we on good standing there? Do we see how I got how I turned that into a negative number? Do we see that or not, guys? I need to know.
Yeah.
Gabe,
Yeah.
you good?
Yes.
All right. So my system is going to be my metal. My metal losing heat. All right. It also, my Q of my metal is also equal to the mass of the metal times the specific heat of the metal times the delta heat of the metal. Is that understood to you? I now know, I'm sorry, go ahead, Gabe.
I said, yeah, it's
Gabe, you good?
Oh yeah, I'm good. I'm good.
All right, so I solved for the Q of my metal. That is what I just simply solved for. That's the negative 1813 joules. Okay? The mass of the metal. I'm going to go back to my original problem. Do I know how much the metal weighed?
Yep.
So I've got the 52.1 grams. The specific heat I'm going to solve for. Now, here comes the tricky part. What was the final temperature of the metal?
We don't know it.
You buy that, Jasmine and Gabe?
Yes.
We don't know what the final temperature of the metal is.
I don't think so.
Okay.
Can't you subtract 28.3 minus 25.1?
Is the 25.1 the original temperature of the metal? Gabe hit on something.
Or would it be 79.8 minus 25.1?
Ah, there we go. The final temperature. If you've been to a Western and you've seen the blacksmith take the horseshoe and throw it in the water, and you see the steam coming off from the water, eventually, is the temperature of the horseshoe the same as the temperature of the water?
Yeah.
So when I give you the final temperature at equilibrium, that's giving you both the final temperature of the water, but it's also giving you the final temperature of the metal. So the final temperature is the same for the metal or the water, or else the water is going to continue to rise in temperature. But it's not, because the experiment says when you get to the highest temperature possible, that's it. That's when the temperature of the metal equals the temperature of the water. You're at equilibrium, nothing further happens. There's no more heat transfer because they're at the same temperature. Does that make sense?
Yes, it does.
So when I am doing this, again, you got to be careful about this. My negative 1813, because that was my temperature of my metal. That was my Q of my metal. That negative 18.13 joules is equal to 52.1 grams times, I'm solving for the specific heat, times 79, was it 79.1? 0.8. So I'm going to take the 1813, divide that by 52.1. And I am going to $79.8 minus, oh, I did something wrong here. This is the final temperature, right, guys? That was the
Yeah.
initial temperature of the metal.
Shouldn't it be 25.1?
No. I'll go show you why not in a second, okay? What was the final temperature, Gabe?
28.3.
All right, the final temperature will be the final temperature of the metal and the water. If you use the 25.1, that's the initial temperature of the water. The initial temperature of the metal is 79.8. So I'm going to take the final temperature minus my initial temperature, and that is going to be negative 51.5. I'm going to take my negative 1813, divide that by 51.5, divide that by 52.1, and I get my specific heat is equal to 0.68 joules per gram Celsius. There's a lot going on in that problem. Do you want me to go over it again, or are we on firm ground here? You tell me, guys, are you on firm ground, or do you want me to go over the whole thing again?
I think I'm okay.
Jasmina, Gabe?
I think I'm fine.
Jasmina?
Yeah, I'm good.
Okay, I'm sorry, I'm just trying to do this. The other way to solve this is to make one big problem. You notice that I have the metal part on the left side, and the negative Q of the metal is equal to the Q of the surroundings. Okay. The negative Q of the metal is equal to the Q of the surroundings. So you can make a big, long problem like this. I think this way is a little easier to understand. Calculate the change in enthalpy, kilojoules per mole, when 0.751 grams of ammonium chloride are dissolved in a constant pressure calorimeter with a heat capacity of 37.1. The calorimeter contains 100 milliliters of water at 205 degrees Celsius. The final temperature is at 19.3. Okay, let's analyze the problem. What is happening here? What physically is happening in the problem? What is the chemist doing? What's physically happening here, guys?
It's dissolving the ammonium.
Okay. You're taking 7.51 grams of ammonium chloride and dissolving it in 100 milliliters of water. Okay. Before you started, the water temperature was 25.0 Celsius. After you added and all the ammonium chloride was dissolved, that temperature decreased to 19.3. So my final temperature is 19.3. I also have the calorimetry constant there. So I'm going to have to deal with that. What am I measuring the temperature of? What did I
The
measure the
water.
temperature of? What? Go ahead, Kevin.
The water.
So why in the world would I use the grams of the ammonium chloride to determine how much heat was transferred? If I'm determining the heat that's transferred, I measured the temperature of the water. So I am going to use the mass of the water. I'm going to hold off on the ammonium chloride for right now. For right now, I want to solve for the amount of heat that is lost in this system. So again, I am going to go with the Q of the water is equal to negative Q of the dissolution. So since it's equal to negative Q of dissolution, I'm going to have my MS delta T for my water, and I'm going to have my C delta T for my calorimeter. My mass of my water is 100 grams. Specific heat of water is 4.184. Now, the tricky part for this question is my final temperature less than my initial temperature?
Yeah.
So I'm going to put my final temperature, the 19.3 minus 25, and my answer overall, is it going to be positive or negative?
No.
This is negative, Kevin, but what am I multiplying it by on the outside of the brackets?
Oh, so bad.
That's why I'm telling you, you got to be very careful about your signs. So I'm going to have the 100 grams times 4.184 times a negative 5.7. To that, I'm going to add my calorimetry constant times the 19.3 minus my 25.0. When I do that, I get and I probably screwed this up.
How did you get 100 grams?
I think the problem gave it.
I saw milliliters.
Okay, all right. What's the density of water, Kevin?
4.1.
Nope, that's not the density, that's a specific heat.
Oh.
Density is
Oh.
a gram per milliliter. So that's where the 100 grams came from. I don't need to play with that. Okay. Sorry, I'm doing this to make it a little clearer. All right. If I multiply my 100 times 4.184 times 19.3 minus 25, I get a negative 23.84. If I multiply 37.1 times a negative 5.7, I get a negative 211. I add these two up, and remember, there's a negative sign on the outside of this brackets. So this number becomes a positive. So that number becomes a positive. All right, now that's the heat of my reaction. That's the heat of my dissolution. Are we good with that?
Yeah.
Okay, that is the heat that was produced by taking 0.751 grams and dissolving it. I want the heat per mole. So the next thing I have to do is I have to figure out the molecular weight of ammonium chloride, divide that into the 0.7151. The ammonium chloride weighs 53.46. I divide that into this 0.751. This means I have 0.0140 moles. I divide the kilojoules from the reaction by 0.0140 moles. This gives me a positive 185.4 kilojoules per mole. Did you understand that last step? Are you guys totally out in left field here?
I understand.
Just me and Gabe?
I think so.
Gabe?
I hope so.
Okay. What I want you to do is I want you to look through the PowerPoints, go through these equations again, and get questions. Give me questions, guys, because I know this is not easy. I know that. But I also know that it's something that you need to get through. We're going to do one more problem, and that may be it for the day. Yeah, okay. We have a 307 gram mineral sample. It was heated to 98.7 degrees Celsius. Placed in a calorimeter containing that much water at 23.6 C. The heat capacity of the calorimeter was 15.7. Final temperature was 32.4. What is the specific heat of the mineral? What's the Q of my surroundings? What's that equal to?
The negative Q of whatever you're solving for. I forgot what the slide said.
Okay, negative Q of my system.
System.
Okay. Fair enough? Okay. But again, I'll ask you, what's this equal to? I'll grant you the first one, Kevin. How do we figure out Q's? What two formulas did I use to figure out Q's?
MS delta T.
M of the water times SH of the water times delta T of the water plus what else?
The C delta.
C of the calorimeter times Delta T of
The water.
the water. Remember, we're using the same delta T's. So all we have to do is go back to our problem. What's the mass of our water? Gabe, what's the mass of our water here?
72.4.
Okay. Okay. What's the specific heat of our water?
Four 4.184.
Thank you. It goes much faster if you answer quicker. Okay. I'm going to make this all on the same. Can you see that, or do I need to make that larger?
I can see it.
I'll go with that. So, what is the change of temperature in my water? Jasmina?
Uh, 32.4 minus
And-
23.
Yeah, okay. Okay. Stop that. Okay, Gabe, what's my calorimetry constant?
Uh, 15.7.
Okay. My temperature difference, what's that going to be? Don't fade on me now, Gabe. What's my temperature difference?
8.8.
32.4.
Oh,
Minus-
minus 23.6.
Okay. So my Q is equal to 2666. Positive number because my final temperature is bigger than my initial temperature. So if my Q of my surroundings is a positive 28.04, what is the Q of my system equal to?
Negative 28.
Again, now we go back to the original problem. I'm being asked for the specific heat of the mineral. So if I know what my Q of the system is equal to negative 28.04 joules, what formula am I going to use here?
The MS delta T.
And the mass of my mineral is
307 grams.
Don't know what that is. What is my change in temperature?
Uh, 32 minus 98.7.
Okay, 1 second. All right, do we have a good sense of these type problems? Guys, you're going to have to work them. You're going to have to work them. I definitely would work the extra homework. You're going to need to know this. Okay? Are you on at least semi-solid ground here? Do we kind of have an understanding?
Yeah.
Basically, as a quick review, you have to realize that the Q of your surroundings is going to be negative the Q of your system. And your system is whatever is happening, whether it be dissolving something in water or having a chemical reaction occur. All right, so you know that the Q of the surroundings is equal to negative the Q of the system. The other two formulas you need to know is that the Q of the water is going to be ms delta T of the water. The Q of the calorimeter is going to be C delta T of the water. The C being the calorimetry constant of the calorimeter, the change in temperature being the change in temperature of the water. You add the calorimeter, the amount absorbed by the calorimeter, plus the amount absorbed by the water. You add those two together. That equals the Q of your surroundings. That's equal to negative Q of your system. And believe it or not, I have another 60 slides to go on this. Where we're going. We're going to go through a little more calorimetry, and then we are going to get into state functions and Hess's law. Mainly, we're going to go through Hess's law on Tuesday. Yes, I am a day behind. I understand that. It will be made up somewhere, and I'm going to have to futz with the quiz dates. It'll be what it'll be, guys. Questions about this? You will have another chance to do the last quiz.
Okay, and then for the extra credit, I thought you said it was due this weekend. For the test two extra credit.
Yeah.
But I just looked at it and it closed this morning. I was planning on doing it right now, but it's closed.
What are you talking about, Kevin? What are you talking about? It's closed on the 18th.
Oh, is it? Okay, maybe I'm crazy. I just tried to go into it.
Wait a second. I just changed it, Kevin.
All right.
So I'm making it open until 9 o'clock on Sunday.
All right, sir. You have a good weekend.
You have a good weekend too.
Don't drink too much.
Talk to me
Thank
about last
you.
night. Take care, guys.
Hey,
My wife and I went out to listen to jazz last night.
oh, jazz is the best.
Absolutely
I
had
agree.
4 saxophones sitting in a terrace bar out in Tierra Verde. Absolutely fantastic views. All the way from do you know the Marriott?
Yeah,
The
Yeah.
top of the Marriott has a bar that on Wednesdays, at least for the next couple weeks, there's a sax quartet.
oh, cool.
So
Where in West Virginia were you from?
I'm from a place called Aliquippa, Pennsylvania. It's about 23 miles northwest of Pittsburgh. I went to school in West Virginia.
I'm moving to Charleston.
Great city. Phenomenal city. The people are going to be friendly there. It's just a great town to be in.
Yeah, it seems pretty active.
Gorgeous area.
Yeah, it is pretty. We went and visited.
Good for you. Just jobs taking you there, Kevin?
Yeah, my girlfriend's job.
Oh.
She got a job at the Capitol.
So you're going to continue your studies up there?
Oh, absolutely. Yeah.
I'm not even sure what schools in Charleston.
There isn't really. There's they have a small West Virginia campus, and then there's Marshall, like 40 minutes away.
Yeah, it's not the easiest road to handle in the winter either, Kevin.
Yeah, I'm not too worried. I lived in Idaho for a year, so I'm not too terribly worried about that.
Good for you. Upper state Iowa?
Idaho. I lived in Coeur d'Alene, Idaho.
Yeah. Oh, so yeah, upper state Idaho is what I meant to say. Yeah, you definitely lived in the mountains there.
Oh yeah. I'm excited to get some weather.
There we go. I can understand that. I envy you in many respects.
Yeah, but I'll also miss the beach.
When you get up through there, you're gonna drive through a place called Beckley, West Virginia. Right outside of Beckley is something called the New River Gorge. Beautiful area. Make sure you hike down to the river.
Okay, I'll do that.
All right. You take care, Kevin.
Have a
Jasmina,
good
you have
weekend.
any questions, Jasmina?
No, not really.
Okay. I will reopen that quiz. All right.
Yeah, thank you.
All right. Take care.
You too. Have a good day.